Started. We are in chapter 26, and last example we did was think 9.4. 9.5 is another estimate, or is another conceptual one. It's not unlike the one that I did in the previous conceptual one, where we had two headlights connected in series and two headlights connected in parallel, and we were supposed to calculate which one put out the most light and estimate or guess which way a car is actually has its headlights wired. So this 9.5 is like that. I'm just going to leave that one up to you guys. I'm going to jump right in though and work on, I believe it's example 9.6. So let me go ahead and share my screen. So that should, yeah, you can see it now. So now what I'm doing is going on to example 26.6. It says a two-speed fan. One way a simple multi-speed ventilation fan for a car can be designed is to put resistors in series with the fan motor. The resistors reduce the current through the motor and make it more run more slowly. Suppose the current in the five motor is excuse me. Suppose the current in the motor is 5.0 amps when it is connected directly across a 12-volt battery. What series resistor should be used to reduce the current to 2 amps for a low speed operation? And B, what power rating should the resistor have? So that's example 26.6. 26.6, and I'm going to write down the information. I'm going to use three sig figs instead of two. So high setting says the current is 5.00 amps, and the low setting is supposed to have I equal to 2.00 amps. And in both cases, we're supposed to have a V that's equivalent to a 12 volt battery. And what we want to know is R for low speed. And that's part A. And part B, we want to know the power rating for R. Okay. So let me give you an idea what the circuit more or less looks like. We have a 12 volt battery. And what's going to happen is we're going to have this go up and run to uh, a couple different ways. Either it'll run directly into the fan motor, which can be written like this. There's the fan motor. It probably has a resistance, which we'll call big R. And what we have is a switch that allows us to switch between that R so I'm going to imagine a switch that goes from here to here, and of course all these other places in between. But one of the other options is that the fan motor, which actually I didn't draw in the best place. Let me regroup on that a little bit. I'm going to draw the fan motor right here, like that. And then we'll have a choice of going directly or going through a resistor like this. So that's our two settings, and this is the resistor R, and this is the resistor big R. So if we flip the switch to the top, it'll go through that that resistance little R. If we don't, it'll skip that little resistance little R and go straight to the power, straight to the battery or the fan motor, excuse me. So now I'm going to use Ohm's law to first out, I'll figure out what exactly R is. So V equals IR tells me that 12.0 volts is equal to 5.00 amps times R, which is the resistance for the motor. So for the fan motor, so R is equal to 12.0 divided by 5.00. So if you wanted to increase that denominator from 5 to 100, I'd multiply by 20. And if I multiply 12 by 20, I get 240. So the resistance is obviously 240, but divided by 100, so that's 240. 2.40 is now the correct amount. That's just me trying to do arithmetic without using my calculator. So I've got that. Now what we want is the total current to go through the battery, including the resistance little r, and we want the total current to only be 2 amps. So now V equals IR gives us 12.0 volts is equal to 2.00 amps. But now instead of resistance big R, we've got resistance 2.40 ohms plus little r, which is what we're trying to figure out. So we can divide both sides by 2 and we'll get 6.00 ohms is equal to 2.40 ohms plus R. So that tells us R is 3.60 ohms. So that's the resistance that we need to bring it down to the lower speed. And the additional part is we need to figure out how much heat will be wasted by this, because that amount of heat is basically what would cause the resistor to fail. And resistor failing could mean a fire, it could mean damage to the motor, all sorts of stuff like that. So you always want to be conscious of that. Now, for part B, we've just did part A, but for part B, we want to figure out what the power is. And the formulas for power are P equals IV, which if you replace the V with IR, you get I squared R. Or also, if you replace the V or the I with V over R, you get V squared over R. Those are the three versions. Again, you want to try to not use something you calculated to calculate a new quantity unless you absolutely have to. And then you want to, use the thing that you're most confident in. So we have calculated the resistance R, and that's probably our more confident number. And what we need to know is what happens when 2 amps go through that. So that's telling me I should use P equals I squared R. So mainly because I have the I and the R. So P sub little r is going to equal I squared times little r. And I squared, of course, is 2.00 amps squared times 3.60 ohms. Of course, 2 amps squared is 4 square amps. 4 square amps times 3.60 would be 14.4. So that gives me 14.4 watts. So yeah, this is particularly important to understand, because it turns out if you go and just grab a random resistor out of a bag of resistors, like ones that uh, used to come from Radio Shack. I've got a ton of them laying around here. Almost all of them are like a quarter watt or an eighth of a watt or a half watt. We're talking 14.4 here, so you can't be using that stuff. So I really like it when your author does these types of problems, because it shows you more about the engineering aspects. It's not only knowing what resistor to put in there, but if you're talking about engineering and building stuff, you have to know what power it can handle as well. Any questions on that one? All right, now we're going to go to a more complicated problem, which is another one analyzing circuits. And this one we're going to do it again the higgledy-piggledy way, which isn't necessarily the best way, but in the next section we'll show you Kirchhoff's laws, and that'll allow us to not use a higgledy-piggledy way. So in this case, it's example 26.7. And example 26.7 says a 9-volt battery whose internal resistance is 0.50 ohms is connected to the circuit shown below. I'm going to draw that circuit for you. So really all we need is that part of the question, and then the actual question is what they're asking for. So it says a 9-volt battery whose internal resistance is lowercase r equals 0.50 ohms is connected in the circuit shown in figure 26.9a. in part A, how much current is drawn from the battery? So we want to know the total current in the battery. So I'm going to call that I sub T for I total, and that's part A. And then part B, they want to know what is the terminal voltage. Your book is calling that VAB, but I like to call it V term. Oops, V term, like that. And then part C, they want to know what is the current through the 6 ohm resistor. So I'm going to call that I6 equals question mark, because if you notice, there's only one 6 ohm resistor on here, so there's no ambiguity in that. Now my job is to draw the actual circuit. And for this circuit, I'm going to draw a battery right here. This is 9.00 volts. Notice I'm using 3 sig figs instead of 2. It goes to an internal resistance right here, which is R equals 0.5. Now, remember, since we draw it next to a resistor symbol, there's no need to actually put the unit on there. That's redundant. You can just put 5.0 if it's 5 ohms. If it's 5 kilo ohms, you put 5.0 K, and so on. Now, after that, the wire runs a little ways upward, and then it hangs a right, and at that right, it breaks off into one leg of the current carrying wire that has a 10 ohm resistor. So I'm going to write that as 10.0. And then it also breaks off to another leg, and this one's the 6 ohm resistor. So I'm going to call that 6.00. But then that leg of the wire breaks up into two parallel resistors. And this top resistance in this bank is 8.00, and this bottom resistance is 4.00. And then these two wires come back together, and then they meet with the wire from the 10 ohm resistor. And then from that junction leaves yet another resistor that's 5 ohms, 5.00. So that's our circuit. So one of the things that helps you, especially when you're doing the higgledy-piggledy method, is to reduce the circuit to as simple as possible. And that means if we reduce all the capacitors to be represented by a single resistance. I said capacitor. I don't know why I said capacitor, but anyways, if we reduce all the capacitors to resistors to one resistor, then we can immediately tell exactly how much current leaves the battery. And if we see that wire doesn't have any nodes before it gets to a resistor, or if it has no nodes between a resistor and the return path on the to the battery, then we know that the current leaving the battery is also the current going into that first resistor that had no nodes, or that last resistor that had no nodes between it and the battery. So that's something else to keep in mind. The trick with reducing these circuits is always try to find two or more resistors or capacitors, if we're doing those, that meet the criteria of being in series or in parallel. You can sort of see in some weird way the 5 ohm and the point 0.5 ohm resistors are in some sense in series, but that's not really the normal way you deal with it, because you'd have to pull one of them through the battery, and that's sort of not kosher. So I'm not going to mess with that, but I just wanted to point it out so you know. But what I do see is the 8 and the 4 are in parallel. And what we know about resistors in parallel is that 1 over R 8.4. Notice I'm using 8.4 to represent the 8 ohm resistor and the 4 ohm resistor. So 1 over 8.4 is 1 over 8.00 plus 1 over 4.00. Obviously, the least common denominator is 8, so I'll multiply 1 over 4 by 2 over 2, and that will give me 1 plus 2 would be 3.00 over 8.00, so that we can see R84 is 8 divided by 3, and 3 goes into 8 two times with 2 left over, and 2/3, of course, is 0.666. So this is 2.667 ohms. So now I can write sort of the equivalent, not showing everything, but I got a 6.00 in series with a 2.667 ohm resistor, and those are both in parallel with a 10.0 ohm resistor, and everything else is the same. So I'll just leave it hanging like this for right now. Now you can see that the 6 ohm resistor and the 2.667 ohm resistor are in series. So I can call this R, let's say 6 2.6. So I'll say 6 2.6 is equal to 6.00 ohms plus 2.667 ohms is equal to 8.667 ohms. So now I can make this equivalent to 110 ohm resistor in parallel with an 8.667 ohm resistor, and that's still equivalent to the last circuit we had. Now, in this case, I'm doing 1 over, I'm going to say 10, 8, 6, because that's 10, 8.6. I'm just not putting the decimal down there because that's a pain in the butt. In this case, this is going to be equal to 1 over 10.0 plus 1 over 8.667. Now, this one is not one that's conducive to easily getting common denominators, so I'm just going to work out what this fraction is. So obviously 1 over 10 is 0.1, so I'm going to say 0.1 plus parenthesis 1 divided by 8.667, close parenthesis, and that gives me 0.2154, and that means R1086 is 1 over that, so I'm going to raise that to the negative 1 power, and that gives me 4.64, and one extra digit is 3. So that gives me 4.643 ohms for that resistor. So now I've completely reduced that top bank, and what we have left is the 9-volt battery and the 0.5 ohm resistor. I didn't need that ohm on there. I should leave it off. And now, instead of having that bank of nasty resistors, I have the one resistance that represents the 4, the 4, the 8, the 6, and the 10. All of them combine to make one resistance whose resistance is 4.643. And then that is in series with the 5.00 ohm resistor. So now what we see is we have 3 resistances that are all in series, the 0.5, the 5, and the 4.64. So I'm just going to call that R equivalent because that's the R equivalent of the entire circuit. And you can see that that's going to be 4.643 plus 0.5 plus 5 gives me 10.143 ohms is the equivalent resistance. So finally, I can say that our battery and circuit can be replaced with the battery and the single resistor of 10.14 ohms. and that tells us what I total is. So applying Ohm's law, V equals IR. Actually, I'm going to write this in red actually, I'm going to write it in blue in the middle. That way I can separate all this work and it not look so confusing. So V equals IR is what I'm going to use. And that means 9.00 is equal to I. Oops, don't have enough room there. So 9.00 volts is equal to I total times 10.14 ohms, like that. And that tells us that I total is equal to 9 divided by that last answer I got. And that gives me 0.8873 amps. So this would be 887 milliamps, for instance. And we now have the answer to part A. The total current leaving the battery is 887 milliamps, or 0.8873 amps. Now, the next part that we want to know is we would like to know the terminal voltage. Now, we did cover a formula for the terminal voltage, and that formula is V term is equal to the EMF of the ideal battery minus the current that the battery is drawing, which we call IT, times the internal resistance. So this becomes 9.00 volts minus 0.8873 amps times zero point 0.5 ohms, like that. And from that, we can see that V term, the terminal voltage, is 9 minus 0.8873 times zero point 0.5, close parentheses. That gives me 8.556 volts is the terminal voltage of the battery. So that's part B. Now, if we look at these separate diagrams, this is the original image, or the original circuit. This is the original circuit with just a little bit of change. This is another one, and this is another one. But what we see is once we figure out how much current goes through this 8.667, that's the same current that goes through the 6 ohms. So if we can figure out exactly how much current goes into the 6 ohm, we then know exactly what that is. We also see that between the battery and this resistor, there's no nodes. There's no alternate routes for charges to go. So one thing we can say, even though the book didn't ask for this, we can say definitively that the current through the 5 ohm resistor is 0.8873. And similarly, there's no nodes between here and here. So the current through the zero point 0.5 ohm resistor is 0.8873. So we now know the current for through two different resistors, and we'll go ahead and solve for the 6 ohm current. So let's do that. Now, what we have is, for instance, this current right here is I total, which equals 0.8873 amps. Now, what's going to come out of this junction right here is what I'd call I10 and what I'd call I6. So I6 is what we're looking for. Now, can you tell me an equation that relates I total, I6, and I10? Either one of you? I'll give you a little hint. Conservation of charge is at play here. All right, the equation that you need to come up with is, notice I total is coming into the junction. That's that point right there. So right here, all the currents going in have to add up to all the currents going out. If it didn't, that would be a violation of conservation of charge. So it means basically I get I get 887 millicoulombs coming through every second in this junction. That means the total milliamps or millicoulombs going through I-10 plus the total millicoulombs going through I-6 has to add up to the point or to the 887 millicoulombs per second. So IT is going to be equal to I-10 plus I-6. So we know that. Another thing we know, though, is that the two currents result in the two same voltages when you have something in parallel with the 10 ohm resistor. So if you look over here, you'll see that when I got to this point, the 10 ohm resistor and the 8.667 ohm resistor were in parallel, and that means that their voltages should be the same. So with that, I can make this other equation where V equals IR tells me that I10 plus I, and I'll write 8.667 for a second, but I'm going to change that because it's the same thing as I6. So I10, or excuse me, I forgot I was writing a multiplication equation, not a additive equation. So I10 times the resistance of the 10 ohm resistor is equal to I 8.667 times R 8.667. But I want to point out or remind you that this current is also equal to I6 because it's the same current. Notice how I'm using different stages of me simplifying the circuit so that I can help myself figure out what's going on. I know that once I reduce the 4 and the 8 to the 2.667, and then that was in series with the 6, I know that whatever goes through that 6 has to go through the 2.667 and therefore also goes through the 8.667. So that's what I'm making use of here. And I really want the I6, not the I10. So I'm going to solve for I10 so that I can remove it. So solving for I10, I get I10 is equal to 8.667 divided by 10.00 times I, and remember that was I 8.667, but it's just the same thing as I6. So I'm doing that. And that tells you, since the resistance is 8.667 and we're dividing it by 10, that should be 0.8867 I6. So now I can plug this into the other equation, which I didn't number and I should have, but let's number it now. This is going to be equation 1 and this will be equation 2. So now I'm going to plug 2 into 1. When I do that, I get I total, which remember we do know that, so that's 0.887 space 3 amps is equal to I10 plus I6, but we just figured out that I10 is 0.88. Oops, that's 86, not 88. Ooh, glad I caught that now instead of screwing up later. So let me fix that again. 0.8667 and 0.8667 I6 plus I6, which by the way equals 1.8667 I6. So now I can solve for I6 by taking 0.8873 and dividing it by 1.8667, and that gives me 0.475. I leave a little space and then a 3 for a non-sig fig, and that's amps. So now I know the current through the 6 ohm resistor. And in fact, I can go farther. I could go ahead and work out all the currents and all the voltages of all the individual resistances in the circuit. And I highly recommend you figuring out how to do that. Feel free to do that as an extra credit and turn it into me, and I'll grade it. I'll try to remember to make a turn-in site for that extra credit, but that's an excellent thing to do. One thing just to get that started, if you look at this circuit now, know that this I6 is the current coming into this little junction right here. So you know I6 is going to be equal to I8 plus I4. And you also know that 8 and 4 are in parallel, so they have the same voltages. So you can write another equation that I8 times 8 ohms is equal to I4 times 4 ohms. And that allows you to solve for I8 or I4 in terms of the other one so that you can plug it into yet another junction equation. Because as I said, I6 is equal to I8 plus I4. So that's one way where you can get both I8 and I4. We can now, for instance, figure out what I10 is just by remembering that I found I10 was 0.8667 times I6. So that's another one we can do. The I5, I already told you, was exactly equal to the current going from the battery, and the I through the zero point 0.5 is obviously the current through the battery. And that's basically it. So give it a try if you can. That should give you a little bit more confidence in working these problems, even uh, when we're using the higgledy-piggledy method as opposed to a more uniform method. So any questions on that? It looks like my answers square up with theirs. They said I6 was 0.48. I was using 3 sig figs and got 0.475. They said the terminal voltage, they were using 2 sig figs, and they said the terminal voltage was 8.6. I used 3 and I got 8.56, so that's good. And the total current from the battery, they said was 0.87. I had the total current through the battery was 0.887, so that's pretty good too. It's off a little bit from what theirs is, but remember they round a lot. So, any questions on that? All right, well, let's move on to the next section where we're starting to use Kirchhoff's laws. So, I want to let you know what Kirchhoff's laws are. So, first off, Kirchhoff, and I'm not sure if that should be pronounced Kirchoff or whatever, but I call it Kirchhoff's law. So, Kirchhoff's rules are as follows. There's really two of them, and one is due to conservation of charge, and the other one's due to conservation of energy. So, Kirchhoff's junction rule or Kirchhoff's junction law, either one, basically says that the sum of the currents in is equal to the sum of the currents going out. So, for instance, if we imagine this is a node where I've got a bunch of currents coming in and going out like this, then we might say this is I1 and I2, and this is I3, and this is I4, and this is I5, and this is I6, and let's say this one is I7. Then Kirchhoff's uh, junction rule would tell you that I1, which comes in, plus I2, which comes in, plus I4, plus I7 is equal to the ones that are left, which is I3 coming out and I5 coming out. And I think that's it. Yeah, it looks like I3 and I5 are the only ones that came out. Oh, I6. So that's Kirchhoff's junction rule. And normally, what happens is whenever you have a circuit, you'll have one extra Kirchhoff's junction rule because one of them is literally just the mirror image of the other. So that normally happens. Expect that. Normally, if you had n junctions, you'd have n minus one equations that are actually useful. Okay. The other one is Kirchhoff's loop rule, and that says the sum of the voltage increases, oops, and decreases add to yield, whoa, that's really bad. Zero. In other words, when you go in a complete loop, and any loop doesn't matter, you're going to have a series of step ups and steps down of voltage. And when you have that, then every step up will be counted as a positive, and every step down will be counted as a negative. You add all those up without counting, a single one more than once, and the sum of all those changes should be zero. That's Kirchhoff's loop rule, and that's the conservation of energy one. It's basically the same thing as when I told you the closed integral of f dot dl was equal to zero. That's the same thing that's going on here. We're calculating instead of f dot dl, we're calculating e dot dl, which is the voltage change. So you're taking the individual voltage steps up and steps down and adding them to get zero. So with that in mind, let's show you how to use this on a particular circuit. And I'm going to start off with the circuit that your book has. This circuit is the example covered in example 26.8. And I'm just going to say, I want to find the currents I1, I2, and I3. So what I have here is one junction on the left-hand side that has a 40 ohm resistor, and then it has an internal resistance that's 0 point, or no, that's 1 ohm, and then it has a 45-volt battery polarized such that the left is the high voltage side, and then you run into another node right there. Now, in addition to that, there's a leg of the circuit that goes up and above all of this, and that has only a 30 ohm resistor. So I'm going to draw the 30 ohm resistor right here. So that's 30 ohms. And I'm going to treat them all like they have at least 3 sig figs, even though I'm not writing it. And then there's another leg down here, and in this leg, it runs into, for starters, a 80-volt battery. And then that 80-volt battery has an internal resistance of 1 ohm. And then I'm going to draw it in a slightly different place because it looks better to me. You have a 20 ohm resistor, and then it runs back into that node. So you see we have two nodes. Remember, the nodes are where more than two wires come together. There's two of them, so that means we should have one node equation because it's always n minus one. What we have to do before we can decide all that, though, is we have to label what we consider current I1 to be, what we consider current I2 to be, and what we consider current I3 to be. And in the example that the book gave you, they went ahead and drew arrows and labels for the three currents. you're not always going to be given that. It's very normal for you to get a circuit like this without being told what currents or what. They would maybe ask you a question, what current goes through the 30 ohm resistor, what current goes through the 40 ohm resistor, and what current goes through the 20 ohm resistor. And that's all they would ask you. They might ask you, does it go to the right or does it go to the left? That's another question they could ask you. Your job is to take the circuit as it looks and try to make a guess at what direction you think the current will be going, and just stick to that direction because it really matters what direction the current's going when you go to use Kirchhoff's loop rule. So I'll show you that as we go. This 80 volt looks like it's really strong. So what I'm going to do is I'm going to assume that there's a current moving to the right, and I'm going to call that one I1. Uh, I suspect it's going to come up here, and that's going to run into the junction where the current going through the 40 ohm resistor is going. And I'm going to assume that that 45 volt battery is going to push that. So I'm going to call that current I2. And I'm also going to assume that I3 is the current going this way. If I'm wrong, what's going to happen is when I solve the system of equations, all the ones that I got wrong for their direction are going to come out negative. The main thing is you got to continue using that negative for all the calculations with those equations, or else you'll get it wrong. Okay, so now that we've got those three equations, or those three currents drawn, and notice the number of independent legs of the circuit is equal to 3, and that's the number of currents that you have. Each wire has its own current, and there's no, there's no two different wires uh, that go through the 30 ohm resistor. It's just one, right? So you got to have that. Now I'm going to write down Kirchhoff's junction rule for the right hand side. What we see is that I1 is coming in and I2 and I3 is going out. So my equation 1 is going to be I1 is equal to I2 plus I3. Notice if you wrote the equation for the other node, for this node right here, you might say I2 comes in, but I2 and I3 comes in, but I1 goes out. In which case you'd say I2 plus I3 is equal to I1, which is exactly the same equation we already have, but it's in the opposite order. So that's why it doesn't matter. Now, what I'm going to do is I'm going to choose the outer loop, and then I'm going to choose I think I'm going to choose the upper loop. That'll be the two that I want to go with, the outer loop and the upper loop. So let's start off with the outer loop. And the big thing here is when you're traveling around a circle on the circuit, if you're going in the same direction of current as the current is, then the resistance will automatically be a voltage drop. So running across the resistor is going to be a voltage drop when you go the same direction as the current. When you go the opposite direction of the current, it's going to be a voltage increase. That's the key thing you got to remember. If you don't remember that, everything's going to mess you up. Everything else is pretty straightforward. Like if you go from the short leg of the battery to the long leg of the battery, that's a voltage increase. If you go from the long leg to the short leg, that's a voltage decrease. So let's say outer loop first. So for the outer loop, I'm going to start in this lower left corner. First off, I run into the negative side of the 80 volt battery and then to the positive side. So that's a increase of 80. So I'm going to say plus 80. Now I have to go through resistance the 1 ohm resistor, and I'm going the direction of the current. So that's a voltage drop. So I'm going to write I1 times 1. That's I times R, in other words. And notice I wrote minus there because I'm going the direction of the current. And now I'm also going to go minus I1 times 20. So that's for the 20 ohm resistor. And now I started from this little dot right here. I'm going this way. and my next stop is this 30 ohm resistor, and then all the way back here. Notice when I get to the 30 ohm resistor, I'm going the same direction as I3, so that 30 ohm resistor is also going to be a voltage drop. So I'll get minus I3 times 30, and now I'm back where I started from, so I'm going to say that's equal to 0. And now I'm going to combine like terms, and I'll get 80 minus 21 I1 minus 30 I3 is equal to 0. I'm going to call that equation 2. Now I'm going to do the upper loop. So the upper loop, I'm going to imagine starting from right here, and I'll just go this way. I'm going to go counterclockwise or clockwise, basically, starting from the node to the right of the 45 ohm resistor. So the first thing I run into is I run into the negative side of a 45 volt battery and then to the positive side. So that's a voltage increase. That means I'm going to put plus 45. I don't have to write physically plus because it's obvious that it's going to be added. But the next thing I run into is the resistance of 1 ohm, and I'm going the direction of the current, so that means it's a voltage drop. So I'll say minus I2 times 1, and then I'll say minus I2 times 40. Now I'm up on the upper leg, so in other words, I've gone from here to here, and now I'm going that way. So notice my next thing I run into is the 30 ohm resistor, but I'm going the opposite direction of the current. So in this case, I have to say plus 30 I3 is equal to 0. Again, combining like terms, I'm going to get 45 minus 41 I2 plus 30 I3 is equal to 0. And that's equation 3. Notice we have three unknowns, I1, I2, I3. We have three equations. That's exactly the way we want it. You can't solve for three unknowns with less than three equations. And if you have more than three equations, sometimes the fourth equation or one of the four equations can actually make it unsolvable. So it's really best when you have exactly the right number. Now, here's the trick. If you notice the equation 2 and equation 3, they both have current I3 in it. So that's kind of nice. And not only that, if you look up at equation 1, that's got I1, I2, and I3 in it. So what in principle we can do is we can solve equation 2 for I1 and it'd be only in terms of I3. And we could solve equation 3 for I2 and it would only be in terms of I3. So by doing that, I could make all the equations 1 into nothing but stuff related to equation to I3. So that's what I'm going to do. Solve 2 for I1 like that. Okay. And when I do that, what I get is I1 is equal to, I'll pull it to the right hand side, and what I'm going to be left with is 80 minus 30 I3, and then I'm just going to divide that by 21. And it turns out this, to me, this seems a lot easier when I just make this up as fractions or as decimals. So 80 divided by 21 gives me 3.810. So that's 3.810 is 80 divided by 21, and 30 divided by 21 is 1.429. So minus 1.429 I3. So that's our equation that I'm going to call 2 prime. And now I'm going to do the same thing. This time I'm going to solve for I2 in equation 3. So solve 3, whoa, for I2. So in this case, I'm going to get I2 is equal to, if I pulled it over to the right, it'd become positive, so I end up getting 45. Oops. I end up getting 45 plus 30 I3 divided by 41. And 45 divided by 41 gives me 1.098. And 30 divided by 41 gives me 0.737. So plus 0.737 or 7317, my fault. And that's times I3. So I've got all my non-significant digits underlined so we can know what they are. There's equation 3. Now what I'm going to do is I now have an equation for I1 in terms of I3. I have an equation for I2 in terms of I3. And I have equation I1 is equal to I2 plus I3. So when I substitute those in, I'll only have I3. So plug 2 prime and 3 prime into 1. When I do that, I get, for starters, I1 is 3.810 minus 1.429 I3 is equal to I2, which is 1.098 plus 0.7317 I3 plus I3. So that's the new equation we have to solve, and it's pretty straightforward because it's only got one unknown now, and that unknown is I3. So I'm going to get all the I3s on one side and all the non-I3 terms on the other side. So if I take 3.810 minus 1.098, that will give me the pure numbers on the left-hand side, and that is 2.712 is equal to, now I'm going to take the 1 times I3 plus the 0.7317 times I3, and I've also got to pull the 1.429 to the right-hand side. It'll become positive when it goes there, so it'll be plus 1.429. So 1 plus 0.7317 plus 1.429 gives me 3.161 I3, and therefore I3 is just going to be 2.712 divided by 3.161, and that gives me 0.8580 amps. So I now have current I3, and now I can use those equations 2 prime and 3 prime to get I1 and I2. So I1, for instance, is going to be 3.810 minus 1.429 times I3, which is 0.8580. So 3.81 minus 1.429 times 0.8580. That gives me 2.584 amps is I1. And then I2 is equal to 1.098 plus 0.7317 times I3, which is 0.8580. That gives me 1.098 plus, I did subtract on the other one, didn't I? Yeah, I did. Okay. So I did that plus 0.7317 times 0.8580. This gives me 1.75, oops, 726 amps. Again, with one extra digit. So that's the way you go about solving systems of equations as well as solving a circuit. Anybody have any questions on that? What did they get? They got for I1, they got 0.87, which, oh, no, they got 0.8. Oh, that's right. They called I1. What was their I1 compared to my I1? Their I1 was the top one. So what I called I3 was their I1. They got 0.87. I got 0.86. That's close enough. What they got for I2, which their I2 was the current going through the 80 volt battery. Ooh, yeah, that's the current going through the 80 volt battery. So that's what I called I1. So their I2 is my I1, and their I2 they found to be 2.6, and I got 2.584, so that looks good. And their last one, they got 1.7, and I got 1.726, so that's all good. Any questions on that? Notice the word part portion that I told you guys is the most important part. So when you're going in a circle to do Kirchhoff's loop rule, if you're at that particular point where you run into a resistor, if you happen to be going the direction of the current that you chose, then that resistance is a voltage drop. If you happen to be going the opposite way, then that resistance is a voltage increase. So you got to put a plus sign there. The other thing to keep your mind on is when you go across the battery, if you go from the short piece to the long piece, that's a voltage increase. If you go from the long one to the short one, that's a voltage decrease. And then, like I said, when you go to actually choose what loops to do, there were three different loops you could have done there. You could have did the outer loop, you could have did the bottom loop, and you could have did the top loop. What I did was the outer loop and the top loop. In doing that, I recognized that both of them, since I did the outer loop and the top loop, both of them would have I3 in it because the outer loop has I3 and I1, and the top loop has I2 and I3. By choosing that so that I have a common one, then I can solve for the one that's not common in terms of the one that's common, and that allows me to more easily solve the system of equations. So that's why I chose the loops that I did. You don't have to choose those same loops. You can choose other ones, but if you choose other ones, then you're going to have to figure out ways to solve them. It is a linear equation, so you can use the Gauss-Jordan method, or you can use the determinants. You can set up matrices and all that good stuff. Whatever you want to do, you have to show me one. At least on test three, for instance, you're going to have to show me one where you solve the system of equations. I don't mind if you use your calculator to check that you got the right answer, but I need to see you do the computational part of solving for the system of equations and two or three equations and three unknowns. So you're going to have to show me that algebra step, or you're going to lose a lot of points on a test for not doing that. So make sure you do that, and that's about it. Anybody have any questions? All right. So the next example they do is to talk about EMFs in series and parallel and charging a battery. And that's important to realize. If you have two batteries and you connect them such that the positive terminal of one battery is touching the negative terminal of the other battery, then you're putting those batteries in series. And what you're getting is, instead of, a 12-volt battery providing 12 volt source. If you had a 12 volt and a 20 volt, like your book has here in figure 2613, and you have the positive terminal of the 20 volt touching the negative terminal of the 12 volt, then what you've made is the equivalent of a 32-volt battery. And that is helpful. You can sort of look at it that's backwards. Sorry about that. I was looking at it the opposite direction for figure B. I thought they had them tail to tail, but actually figure A is where they have them head to tail, like I was talking about. So figure A has 1.5-volt battery. It's got its positive terminal touching the negative terminal of the 1.5-volt battery. This is what you see in video games and computer mouse and flashlights and stuff like that, where you take one battery and stack it on top of the other battery, where the positive end of this one is touching the negative end of this one. That gets you, in this case, it was 1.5 plus 1.5, so you get 3 volts. So when you pull out two batteries stacked up like that from a flashlight, you can say, oh, well, I know that the flashlight runs on 3 volts. If you ran into four of them, it obviously runs on 6 volt. If you ran into eight of them, it would obviously run on 12 volts, so on and so forth. When you do the 20 forced into the 12, where the positive terminals are touching each other, that tends to charge a battery, but it's kind of dangerous. So you got to be careful. Your book talks about that. You can find online where people will show you videos of how to charge regular batteries, and there's some truth to being able to charge them a little bit, but there are limits to what you can do. And not only that, it's very time consuming and it's very risky, because when you force charges into one battery by another battery, the batteries are going to get hot. And when they get hot, things could happen. So, what often is done on these videos is they'll have like a little timer where it will they'll basically only allow current to come from the charging battery into into the battery that's being charged for, like, 30 or 45 seconds, and then it'll stop for 2 minutes, and then 30 or 45 seconds it'll do it again, and then stop for 2 or 3 minutes, something like that. And I'm not saying those numbers are safe. I'm just telling you as a example, these are kind of numbers that we might use, but I'm not sure that they would work. You just got to be mindful of it. So I wouldn't recommend doing that unless you really are desperate and just need to charge a battery. The final thing that your book shows in that figure 2613 is two batteries in parallel. When you have that, basically that says, hey, I don't need a higher voltage than my battery supplies. So, for instance, if I use two AA batteries in parallel, I'm running on 1.5 volts, but I'm putting them in parallel. So basically, you can sort of think of it as I'm only draining the batteries half as brutally as I normally would. Because if I just stuck one battery in there, it would take all the battery would supply all the current. But if I put two of them in parallel, then each battery delivers half the current. So you're saving a little bit of energy, that sort of thing. Any questions on that? All right. I don't think I need to go ahead and do this example with the example 26.9. I'm just going to tell you guys to make sure make sure you can solve example 26-9. Uh, I've given you all that you really need to know. I've shown you how to do all this stuff. I've told you specifically how to choose what loops you're going to use and for what reason. And I told you how to deal with resistors and batteries as you cross them in Kirchoff's loop rule. So I don't see much use in it. And besides that, if you want to actually see this one work by me, there's a ton of videos of me doing that. Just do a search for solving circuits in my YouTube channel and you'll find a ton of them. Plus, I have some in our modules that you can look at. I want to go on to the next part, which is where we're going to discuss basically a RC circuit. So if, for instance, let's start here. This is RC circuits, resistor and capacitors in series. Whoa, Nelly. Resistors and capacitors in series. So we start off with a fairly simple looking diagram. I'm not going to do the derivation. If you want to look for the derivation, I've done that a ton of times on my YouTube channel. But what we're looking at here is you have a battery. So there's our battery. It has an EMF. It's like an ideal battery, basically. It has an EMF given by E, and it goes down and runs into a switch, and then that switch goes up and runs into a capacitor like that. And then you can either think of it as a separate resistor, or it could be thought of as the total resistance of the wire, or you can think of this R value as being the resistance of the resistor plus the resistance of the wire total. That's another way of looking at it. C is the capacitance that you have there, and R is the resistance that you have there. Now, what's going to happen is when you close that switch, then positive particles, remember we pretend conventional current is the real thing, so positive charges are going to flow around and you're going to start getting positive charges building up on the bottom plate of this capacitor. Now, each time a positive charge builds up on that plate, it's going to compel a positive charge to leave the top plate, and you're going to get a negative charge there, a negative charge here, negative charge here and a negative charge here. And then those negative charges, just like the positive charges across from it, those negative charges will stay there because they're attracted to the positive charges. But the positive charges are going to continue running around. They're going to go through the resistor and then return to the battery. At least that's going to happen until basically the battery has exactly the same voltage on the positive side as the positive side of the capacitor. So, in other words, if it's a 12-volt battery, if you touch the side of the capacitor that's on the bottom there and it reads 12 volts, then it's fully charged. And you'd expect to read, in fact, 0 volts on the negative side of the battery as well as 0 volts on the top plate of the capacitor. Okay. But that's the way that works. If you wanted to actually work this out, you could use Kirchhoff's loop rule, and Kirchhoff's loop rule would tell you that you have increase in voltage given by uh, E, and basically we're going from the top left corner around, and we're going to then subtract from it the voltage of the capacitor. Remember, capacitance is given by C equals Q over V, so V is equal to Q over C. So that capacitor, notice we're going to run into the positive plate first, just like we ran into the positive plate of a battery first, and then the negative plate. That means there's a voltage drop. So this voltage drop is going to be the charge on the capacitor divided by the capacitance itself. And then we're going to, again, going in the direction of the current, the resistance is going to represent a voltage drop. So that's going to be I times R. And then all of that is equal to 0. Now, the big thing to remember is that I is technically dQ/dt in this case. When you're discharging a capacitor, though, the I is actually going to be negative dQ/dt because the charge Q on the capacitor, as it gets smaller and smaller, the current gets larger and larger. So in that case, it's going to be the negative. But what we get here now is basically that E is equal to I can pull them on the opposite sides and they'll be positive, and what we're going to get is R dq dt, because that's R times I, plus 1 over C times Q. So that's actually a differential equation. We could solve that differential equation. It's separable differential equation, so it's pretty straightforward. Your book does that for you. And what you end up getting is is Q. Q is equal to C times E, which obviously that's just from Q equals C times V, basically. That's going to be C times E times 1 minus E to the negative T over RC. And RC is called the time constant, also called tau. So we could also write this, for instance, as Q0 times 1 minus E to the negative T over tau, like that, where tau is defined to be RC, almost 1 over RC. So if you actually take the time and work out the units of R times C, farads times times ohms, you'll find out that that's actually got the units of time, and that's part of what we need to know. Now, additionally, we can find the voltage because the voltage is given by. I'm going to go ahead and circle this so you'll know which equations are useful. We've got to use that one. We've got to use that one. And we're also going to use the voltage across the capacitor is equal to basically the battery voltage that it can reach possibly times 1 minus e to the negative t over RC again, or t over tau, either one would be fine. So that's another equation we're able to use. And we could also get the current by taking the derivative of Q with respect to time. So I is equal to dq over dt. And when you compute that, you can see that the C times E, in taking the derivative, it's C times E minus C times E to the negative T over RC. The C times E term is just going to disappear, but the C times E, I hate this app here, it's driving me crazy. C, negative C times E is for the second term, and then I got to take e to the negative t over RC, but now I got to take the derivative of negative t over RC with respect to t, and that's, of course, negative 1 over RC. So from that, you get I is equal to, you can see that the c's cancel out, and we end up getting E over R times e to the negative t over tau. So that's the charging equations. So those equations are used for charging a capacitor. After that, you can actually look at the example if you want. I'm running out of time, so I'm trying to make sure I cover enough so you can go ahead and get started on doing your homeworks. If you now take another circuit, this time with a charged capacitor instead of a battery, then what you get is something like this. Like here's a capacitor of capacitance C that has a voltage V0, and in fact, it's positively charged like this. And you're going to connect that, for instance, to a resistor through a switch. So there's your resistance R, and you can imagine the switch going like this. And in this case, you end up getting from Kirchhoff's law, basically you end up getting a change in voltage. If I wanted to take a voltage increase, for instance, I could start at this point and go this way, and then my increase in voltage would be Q over C. So I'm going to say Q, oops, might hopefully use the right pen. I'm going to say Q over C, and then I'm going to say minus I times R is equal to zero. That's Kirchhoff's loop rule. Now, that also gives us that IR is equal to Q over C. And in this case, this is where I was warning you, I is actually negative dq dt. So now I get negative dq dt times R is equal to Q over C. And again, that's another differential equation you can solve. When you solve it, though, you get a little bit simpler expression. In this case, you get Q is equal to Q0 times e to the negative t over tau, the exact same tau we had before. We get V for the capacitor is equal to V0 times e to the negative t over tau again. And for the current, I, you get I0 times e to the negative t over tau again. And again, tau is just the same old RC that we said before. All right. So these are the equations for discharging a capacitor. I think you'll find they're pretty straightforward to apply in the examples. So I'm going to go ahead and call it a day. They do examples 2610 and 2611. And you can ask me questions about it next time. I'll probably work at least one of those, and I might even work one where I use a ammeter or a galvanometer to design an ammeter and a voltmeter. So that's about all we have left. You can pretty much do all the homeworks at this point, though, except for ones with ammeters. And I think I've already cut all those out where we're using a galvanometer to make it a ammeter or a voltmeter. That's a neat process, and it's something I like doing with my students and teaching them how to do. So I'll plan on teaching that next time, and then we'll jump right into chapter 27 in our next meeting. So. Keep an eye out for your emails in case I send you a video to watch. I plan on sending a video to help you help us catch up, and you're going to watch that and then have watched it already by the time I attend the next class. So keep an eye out for your emails so that you can watch it if I do send you one. I have very little time, but I can take questions for a few minutes. I have to proctor a test at 7, so you got a couple minutes if you have anything.